Hi, this is Professor Dorr, and this is lecture number 2 of EE 310. In this lecture, we're going to discuss initial conditions and Ohm's law. Initial conditions are covered in Chapter 8 of Alexander and Sadiku, and they tend to be one of the more difficult subjects of EE 310. I really value Chapter 8 because what it does and what all this initial condition stuff does for you is it shows you how to look at circuits and figure out what they do. And it really helps develop that intuition that'll help you with circuits, whether they have transistors or MOSFETs or integrated circuits or RF circuitry. It really teaches you how to look at circuits and just figure out intuitively what they do. And that, of course, helps you analyze them and design them and improve them. I include Ohm's law in this lecture because I know that you all know Ohm's law. Right up here, you know that V equals IR. You've used it quite a bit. You've written a lot of mesh equations and a lot of node equations. But as I mentioned in the last lecture, I'm going to take Ohm's law from here and I'm going to try to put it down here. And we're going to do that with our KVL on the fly and KCL on the fly. We're going to do a couple of little examples, and I'm going to show you some things about voltage sources and current sources, because I really want to pound that information into you so it just helps you be a better engineer and do better in the class. So let's get started. I want to look at what is a current source and what is a voltage source. And of course, you've seen lots of current sources, you've seen lots of voltage sources, you've made lots of Thevenin equivalents and stuff. But what I want to do is I really want to look at what they really do. And let's start off with a voltage source. Now, what a voltage source does, if we look at it intuitively or verbally, we can say that that voltage source will put out whatever current it needs to maintain, in this case, 5 volts at the output. So if yeah, Bella, I hear you. Sorry about that. So if I put a 1 ohm resistor on the output of this, I am going to get 5 amperes. If I put a 1 micro ohm resistor right here, I'm going to get 5 million amperes, because the voltage source intuitively and verbally will put out whatever current it needs to make sure that there's 5 volts here. Let's look at that with a graph. I like to look at current versus voltage plots. And in this case, you need to stop that. You need to stop that, Bella. And here's a current versus voltage plot. And here are all the operating points for my 5 volt power supply. And what it shows you is that this power supply will give you 5 volts at any current you want. You just keep on going. Now let's look at a current source. And the way I like to think of a current source intuitively is it will put out whatever voltage it needs such that the current coming out of that source is the specified value. In this case, our current source is 3 amps. And so if I put a 1 ohm resistor on the output of this, I'm going to get 3 volts. If I put 1,000,000 ohms here, I'm going to get 3 million ohms, 3 million amps. I'm sorry, 3 million volts. I can do this. And so that's the verbal description of what a current source does. And now let's show it on my IV characteristic curve. And I can see that for the current source, the current is going to be 3 amps, and it'll put out whatever voltage it'll need. It'll put out positive voltage, it'll put out negative voltage. just like my voltage source will put out positive current, it'll put out negative current. So when you look at a voltage source or a current source, I want you to think of them this way. So let's do a couple of little problems with voltage and current sources. And I'm also going to introduce a little bit more terminology. So in this circuit, we see my little ground symbol here. You see this in schematics all the time. Sometimes you see it as the three little lines that make the earth ground, or sometimes you just see it as a ground like this. In many systems, you'll have different grounds. You might have an analog ground and a digital ground, but the bottom line is they use the little symbol so they don't have to draw an arrow or a wire every time. Like, for example, if this were a big complicated schematic, I know a lot of things go to ground, and I don't want to have to connect wires between all those grounds, so I'll just use the ground symbol. So that's ground. Now here, I'm showing just plus 5 volts, and I'm not showing a plus and minus or anything like that. I'm just saying this goes to plus 5 volts. Again, this is a convenient thing for schematic diagrams in industry because they get pretty complicated and a lot of things will go to the same voltage. So it's easier to just have this little reference here saying this connects to 5 volts. And I use that notation in this class. And so 5 volts with respect to ground. Now here I have this line, and it goes nowhere except to this little V. And what this is I call this kind of a sniffing point. This is a line that shows where voltage V is defined. So no current goes through this line. You'll hear me call it a sniffing point in the class. That's a little bit informal, but it's a good piece of informality. So what I want to know in this problem is with 5 volts at the top and 5 ohms and 2 amps here, what is the voltage at this point right here? And sorry, this kitty cat is just driving me nuts. She won't let me pick her up, but she's meowing and walking around my feet and putting her tail up and doing all the kind of things that kitties do when they want attention. But she doesn't want to get picked up. Bella's mom told her, because she was feral, to not trust the humans. And at 13 years old, Bella hasn't figured out that the humans aren't all that bad. Okay, so we have our problem here with our current source. And I know that this voltage source is going to put out 5 volts, regardless of the current coming out of it. Here it is on the curve. And I know my current source is going to put out 2 amps, regardless of the voltage. So what I'm going to do here is I'm going to use what I call KVL on the fly again. I'm going to say that this 5 volts is really nailed down. It's not going to change. I like to think of this as having 1 foot nailed to the floor like a basketball player when they're looking for who to pass the ball to. So 5 volts, that's an absolute here. Well, I know now that I got 2 amps here. I have no current here because this is just a sniffing point. So that means I have 2 amps going through this resistor. We just used KCL on the fly. We said that this 2 amps comes out of here. It's not going there, so that means it's all got to go there. Now let's use KVL on the fly. I know that I start at 5 and I am going to go up 2 amps times 5 ohms. Or in other words, this point is nailed down and I know that this current source is going to give me 2 amps going this way. So plus to minus, I'm going to get 2 amps times 5 ohms or 10 volts. So start at 5. Go up 10, I got 15 volts right here. Does that make sense? Yeah, because the 2 amp current source will put out whatever voltage it needs in order to get that 2 amps out. In this case, it needs to put out 15 volts. So if this was actually 2 amps, we'd be somewhere over here for our operating point. Or actually on this graph, 2 amps would be here, 15 volts would be about here, and that would be our operating point for our current source. Our voltage source here, it is accepting 2 amps. So our 5-volt voltage source has a current of -2 amps. So there's some positive and negative signs floating around here, and you may want to stop the lecture and make sure you're really comfortable with that, because we're going to use this over and over in this class. Let's look at another problem. In this problem, I've got a ground symbol, I've got 3 ohms. Hey, look here, I didn't even draw the line coming off. I just labeled the point V, and that's the voltage I'm looking for. Let's see, we've got 7 ohms, we've got a current source, and then we've got something we've never seen before, which is at one end of the current source, I just drew a squiggle. And I did that intentionally. And here's why. Because that current source is going to do whatever it has to do to get 2 amps of current right here. So do I really care what's under here? I really don't. And that's why I drew it as a squiggle, because I want you to look at that and go, huh? And then figure out, oh, it doesn't matter. So let's use our techniques here. We're going to use KVL on the fly. Actually, let's use KCL first, which just says I have 2 amps coming in here. That means I got 2 amps here. That means I got 2 amps here. So the 2 amps through this 3 ohm resistor is going to give me 2 amps times 3 ohms. That's a voltage drop of 6 volts plus to minus. Now let's use KVL on the fly. Start at 0, go up 2 times 3, 6 volts, and I have 6 volts. Or in other words, 2 amps times 3 ohms. But this end is nailed down, so this has to be at plus 6. Okay, let's do another one. What do we have here? We have a voltage. Oh, wait, we can do more with this one. I'm sorry. What's the voltage at the current source output right here? And it's going to be, let's see, 2 amps times a total of 10 ohms. So 2 amps times 10 ohms is 20 volts. And that means I'm 20 volts from here to here. Now let's use KVL on the fly. The ground is nailed down at 0 like that basketball player's foot. So 0, go up 20, I'm 20 volts right here. So where's my operating point? I am 2 amps, let's say that's about here, and 20 volts. So that's the operating point for this problem here. Now let's look at this one. We have a voltage source, we have a 1K resistor, and we have a 1 milliamp current source. Somebody actually gave me this little problem on a job interview once, and I did the problem and then asked the person if I could use it for my lectures because I thought it was such a cool little example. So let's see, we've got 1 milliamp here. Looks like this time I grounded the current source. If I wanted, I could have made the current source go to 1,000,000 bazillion volts, but I didn't. I just made it go to ground. And so let's look at this. We have 1 milliamp. So 1 milliamp times 1K means I'm going to have a voltage from plus to minus of 1 volt. Plus to minus. So let's see, start at ground, go up a volt, go down a volt, and VA is equal to 0 volts. So please go back and review these problems. These will help you with this class. They're really going to help you with EE330, where you get into transistor circuits and MOSFET circuits, where the MOSFETs and transistors look like current sources sometimes, and they look like voltage sources other times. And if you can just go back to this one picture right here, you'll always remember and have an intuitive idea about what your current sources and voltage sources are doing. In the last lecture, I introduced the rules, capital R for those rules, because these are some of the few absolutes that we really get in EE310. But these rules will always work. And sometimes students will do a couple of problems and say, hey, professor, I figured out another rule or something. And sometimes they do come up with a nice variant of these rules, but other times the rule that they come up with is not really correct. It works for those two problems, but may not work for all problems. Some of the rules you guys come up with are pretty clever, and I can't wait to see what you all do when you go out into industry, because you're going to come up with some good rules for different things, and that'll be fun to watch. But these rules will not change. They come with a guarantee. I guarantee these rules work. So I like to divide them up where I have a verbal side for whichever side of your head does verbal things, and an equation for the mathematical side. What I'll do is, as I'm triaging problems, I'll use that verbal side to get my bearings, and then I'll jump into the math and get my hard answers. So I'll go through them a little bit faster than last time. So for an inductor, the current in the inductor cannot change instantaneously. You might remember we tied this back to the current being related to the magnetic field, and that's where the energy is stored, and we can't change the energy, we can't move energy instantaneously. But to get through EE310, the inductor current cannot change instantaneously, and this will get you a long way. Mathematically, we're going to say that the inductor current at time 0 plus is equal to the inductor current at time 0 minus. Or in other words, when we make this topology change in the circuit at t equals 0, which if you're not familiar with that, go back to the last lecture because we went through that. When we make that topology change, the inductor current after the change is equal to the inductor current before the change. Now, that's only at time 0 minus and 0 plus, because of course, when the topology is changed, the inductor current is going to change eventually. But right at that instant when that switch changes, that current isn't going to change. Our next rule, the capacitor current voltage cannot change instantaneously. For the inductor, we said the current can't change, but for the capacitor, the voltage can't change instantaneously. And we connected that back to saying, well, the voltage across the capacitor makes the electric field between those two parallel plates. Capacitors store energy in their electric field, and you can't take energy from one place and put it somewhere else instantaneously. But we're just trying to survive doing all these problems right now. So this is a really good rule, and we'll use it quite a lot. Mathematically, we have the voltage on the capacitor at 0 plus is equal to the voltage on the capacitor at 0 minus. So at that topology change, the capacitor voltage will not change. It will eventually change, but right at the instant of changing, it will not, the voltage will not change. So here are our cannots. Let's look at our cans. The inductor voltage, it can change instantaneously. So from t equals 0 to 0 minus to t equals 0 plus, yeah, we can have a big change in the inductor voltage. And the way I describe this mathematically is I just gave the equation for the physics of the inductor, which is V is equal to L di dt. Our next rule is that the capacitor current can change instantaneously. And for this rule, I just, again, wrote the equation and said IC is equal to C dV dt. So what this kind of shows you is dV dt can change instantaneously because it's equal to just IC over C. But V cannot change instantaneously. Just like here, di dt can change instantaneously. It's equal to just V over L, but the current can't change instantaneously. Now we go to our steady state rules, and in steady state, di dt for the inductor for any piece of the circuit, and I should just reiterate that when we talk about steady state, that means that d anything dt is zero. That means di dt is zero for every component in the circuit. dV dt in the circuit is zero for every component in the circuit. Now, of course, at steady state, components can have current through them and then they can have voltage across them, but it can't be changing. So I like to think of steady state as d anything dt is equal to zero. And so in steady state, we have di dt equals zero. So here's our equation for the inductor. We can just see it up here. Since di dt is equal to zero, the inductor voltage is zero. So at steady state, no voltage across the inductor. Similarly with a capacitor, in steady state, you have no current through the capacitor. And just one more comment about steady state is, remember we said that for the kind of problems we're doing in Chapter 8, the circuit sits in a topology for a long, long time, meaning that it comes to steady state. So d anything dt is equal to zero. Then we do some topology change. We close a switch, we turn on a voltage, something like that at t equals zero. And we get a, or more realistically, we get a thud, thud, or a thud, thud, or we get a boing, boing. But the circuit again ends up in steady state at time infinity. So we have steady state, transient portion, steady state. And these two rules give us what we need at steady state, namely the inductor voltage is zero, the capacitor current is equal to zero. Okay, let's do some problems. So again, I like to triage these problems before I really jump into the math. I really want to figure out what's going on. And this, as I mentioned at the beginning of the lecture, is just some of the greatest value of this chapter, because you have to look at a circuit and say, what's all this stuff doing? When you're in industry and you look at a circuit like this, sometimes you'll just need a cursory knowledge of that circuit. You just kind of want a general idea of what it does. Other times, you'll have been asked to fix this circuit or redesign this circuit, and then you'll follow your triage with a deep dive so that you can find the most appropriate and best performing and least expensive components that you can. But let's start off by triaging. First, we have our switch here. And what this symbol and the t equals zero tell us is that the circuit has been sitting with the switch open for a long time. It has come to steady state, and that switch is going to close at t equals 0 and stay closed. All that in that little symbol. That's what engineers do. We're good at that. So at time equals 0 minus, switch is going to be open, and then at t equals 0 it closes. Let's see, we see a series circuit. So one thing that tells me is that the current through everything in here when that switch is closed is going to be the same. What else do I see? I see VB. Ooh, that must mean VB with respect to ground. He better have showed the ground, otherwise VB doesn't mean anything. Ground will typically be on the bottom. But you got to find it. You got to make sure you see it there. Let's see, I defined a VC here where I said, okay, VC is going to be the voltage across this resistor from plus to minus. All right, and I'm showing I. And of course, this I is the same as this I is the same as this I, but it's all right here. Okay, so at t equals 0 minus, what's the current going to be? Let's see, obviously it's going to be 0 because the switch is open. Okay, so if the switch is open, then I'm going to have no current path. So that means I got no voltage across the inductor. And since I'm at steady state at t equals 0 minus, I have no voltage across the inductor. So KVL on the fly says I got 0 here, I got no voltage across here, so VA is going to be 0. I got no current through that resistor because the switch is open, so that means VB is going to be 0. Colloquially, you might say, oh, that thing's dead, nothing's connected. Yeah, that's reasonable. But I used the rules to show what dead was for this circuit. So let's see, we know our voltages and our current at t equals 0. So now let's look at what happens when this switch closes. So when it closes, this guy's a voltage source. So I got 5 volts here, period. This is a voltage source. I close that switch. It'll do whatever it needs to put 5 volts right here. Okay, let's see. We can't change the current in the inductor immediately, instantaneously. The current at t equals 0 minus was 0, so that means when I close the switch, the current is still going to be 0. So if there's no current, that means I have no voltage across this resistor. So I got no voltage drop. So let's see, 5 volts, 5 volts, 5 minus 10 ohms times 0 amps gives me 5. Or in other words, no voltage drop across the resistor. So if I got 5 volts here, I got 5 volts here. So at t equals 0, I got 5 volts right here, 0 plus, I'm sorry. And I go back to my rules and I say, oh, I can change the voltage across the inductor instantaneously. So the voltage across the inductor jumped from 0 volts to 5 volts at t equals 0 plus. It's kind of cool. But you also notice that I was able to check my work with my rule that said I can change the inductor voltage quickly. So all my rules going down the line are satisfied, except for the ones that have capacitors in them, because there's no capacitor here. Now let's go to t equals infinity. So this switch has been closed for a long, long time, meaning the circuit's come back to steady state. What do I know? I know I got 0 volts across the inductor, and so that means I got 0 volts here, so I got 0 volts here, okay? 5 volts minus 0 means I got 5 volts across this resistor. So 5 volts over 10 ohms means I have a half an amp. So I have a 1/2 amp going through this circuit. I got a voltage of 0, 0, 5 volts, because that's what this voltage source is going to do. I got a 1/2 amp going through here. So I'm really comfortable with this. So in our triage, we just solved everything that you see right here. And our triage was really good enough to do it. Though if I want, since now I've triaged it and I kind of know what's going on, I could quickly write all these in. In fact, let's do it. I of 0 minus, it's going to be 0 because the switch is open. I of 0 plus is going to be 0 because you can't change the current in the inductor instantaneously. I of infinity, no voltage across the inductor at time equals infinity, so I got 0 volts here. I got 5 volts here because the switch is closed. So 5 volts divided by 10 ohms, it's a 1/2 amp. VA at 0 minus, no voltage across the inductor. So KVL says start at 0, go up 0, VA is 0. VA at infinity, no voltage across that inductor at steady state. So VA at infinity is going to be 0 also. VB at 0 minus. Well, at 0 minus, we know we have no current, and that means we have no voltage drop across here, and we know the voltage here is 0 because there's no voltage drop across the inductor. So we start at 0, we go up 0 because there's no voltage drop across the inductor at steady state, and now we go up 0 amps times 10 ohms, that's another 0, so VB is 0 at time equals 0 minus. At time equals 0 plus, this is connected, I'm connected to a voltage source. VB is 5 volts at 0 plus. VB at infinity, it's connected to a voltage source, it's 5 volts. Now let's look at VC. And VC, you see that it's carefully defined here. At 0 minus, we have no current in the circuit, so VC will be 0. At t equals 0 plus, I'm going to go to my inductor and say the current cannot change instantaneously, so the current's still going to be 0. And so I have 0 volts for VC of 0 plus. VC of infinity, I got 5 volts here. I got 0 volts here. Looks like 5 volts for VC of infinity. Now I want to find di dt at 0 plus. You might ask, why are you so interested in this derivative? And you'll see that this is what we need to solve the differential equations for these circuits, and that's why we do it. So di dt at 0 plus. Well, I know that in order to get di dt, I'm going to use the equation of V, and I said VA, but that's really the voltage across the inductor, equals L di dt at 0 plus. Remember here, I'm asked for di dt at 0 plus, because it'll immediately change after that, but I want it at 0 plus. So here's my basic inductor equation of V equals L di dt. So di dt is equal to V over L. And so what is that going to be? Well, remember we said that at t equals 0 plus, the current here won't change, but the voltage can. So at 0 plus, we're going to be 5, 5, no current, so no voltage drop. 5 minus 0 is 5. So VA at 0 plus right here is going to be 5 volts. So di dt at 0 plus is going to be 5 divided by 2. I think that's 2.5, right? Is going to be di dt. Okay, thankfully, Bella has gone to sleep, so she's not pestering anymore. She's actually curled up down at my feet. If you're getting tired and sleepy, take a break. This is hard information. These are difficult examples, and we're going to go through a bunch more of them, and I really want you to get your money's worth out of these. So let's look at our next example. So in this example, we have a current source, and the current source is at t equals 0 minus. The switch is going to be closed, so this current source is going to be squirting current through here. Let's see, there's no current through a capacitor at DC. That's one of our rules. So KCL on the fly says that 1 amp is going to go right straight through here and through this resistor. So some of you might be tempted to draw this capacitor as two little open stubby things here to show that there's no current going through it. That you can do that, and that's fine, but I like to leave the capacitor in there because I want to be able to look at the circuit when we change from t equals 0 to 0 minus to 0 plus. And if you have the rules ingrained in your head, you'll do what I just did and just say, okay, the current's going this way. None of it's going through here at 0 minus because we're steady state, so it's all going through here. And we have 1 amp times 4 ohms is going to give us 4 volts at t equals 0 minus. And at t equals 0 plus, this switch is going to open. Now, if you go back to my definition of the current source, you can see that the current source isn't going to be very happy with that. It's going to put out a bazillion volts in theory. But we're not going to worry about it because the switch is going to be open, though I will show you a better way to represent that in just a little bit. So at t equals 0 plus, we're going to have 4 volts here. That means we're going to have 4 volts sitting on the capacitor. And now the capacitor voltage can't change quickly. So therefore, it's going to instantaneously put 1 amp through this resistor. Why? Again, the voltage across the capacitor cannot change instantaneously. And so therefore, in order to maintain that voltage, it's going to have to feed this resistor with 1 amp. And it can do that because remember, the current through the capacitor can change instantaneously. Okay, so now let's look at time equals infinity. So at time equals infinity, I know that this capacitor will again have no current through it. And so let's see. Time equals infinity, switch is open, so I got no current here. Capacitor's at steady state, so I got no current here. That means I got no current here. That's KCL on the fly, I just did it. No current here means no voltage across this resistor. So now let's use KVL on the fly. Start at 0, go up 0. V sub r is going to be 0 at time equals infinity. And since the voltage here is 0, IR is going to be 0 at time equals infinity. So now I've triaged the problem and I'm pretty comfortable with it. Let's look at it more formally. The voltage at the resistor at 0 minus, I have no current, so I have no current. I'm sorry, at 0 minus I have 1 amp coming out of here. I have 1 amp going this way, I got nothing going this way, I got 1 amp going through 4 ohms. So I'm going to start at 0 and go 0, go up 1 amp times 4 ohms. I got 4 volts right here. That's VR equals 0. VR at 0 plus. So here I'm going to look to the capacitor and say that at t equals 0 minus, I have 4 volts here. That means I have 4 volts here, which means the capacitor has 4 volts on it. And that voltage cannot change at 0 plus. So therefore, VR at 0 plus is going to be the same as VC of 0 plus. It's going to be 4 volts. VR at infinity, remember at infinity, the switch will have been open for a long time. So I got no current here. Capacitors at steady state, so I have no current here. That means I have no current here. That means I have no voltage drop across my resistor. So 0, go up 0. VR at infinity is 0. IC at 0 minus. Well, that's easy. We know there's no current through a capacitor at DC or at steady state. IC at 0 plus. Got to be careful here because we know we can change the capacitor current quickly. So let's look at 0 plus. We have 4 volts sitting on this capacitor, and at t equals 0, that voltage can't change. So that means in order to maintain this voltage, it's going to have to put 4 divided by 4, or 1 amp, through this resistor. So the current through the capacitor at t equals 0 plus is going to be negative 1 amp. See how we defined the capacitor current? It's defined going this way as positive, but it's going this way, so it's negative, so it's negative 1 amp. IC of infinity, that's a duh. The capacitor is at steady state, so there's no current, so it's 0. So now I want to look at dVR dt, or in other words, the change in the resistor voltage with respect to time at time equals 0, 0 minus. So we remember that t equals 0 minus is a steady state. And so therefore, d anything dt at steady state is 0. Now let's look at dVR dt at 0 plus. And I'm throwing a little banana peel at you here because I'm saying I want dVR dt at 0 plus. But in order to get that, I really need to look at the capacitor because dVR dt is the same as dVC dt. So it would have made the problem easier if I asked for just dVC dt, because then I could go right to the formula of I equals C dV dt and use it. But I said VR because I want you to see that these voltages are the same. So let's use our formula. IC at t equals 0. Why IC? Because I really care about the capacitor here. That's the dV I want, dV dt that I want. So IC at t equals 0 plus equals C dV dt at 0 plus. So we solve that for dV dt, and it's just IC over C. And IC we said was negative 1 amp, so it's going to be negative 1/2 amps per volts per second, negative 1/2 volts per second. Now I want to get DIR dt. And again, we got to really look at what we're being asked for here. DIR dt. Well, isn't that going to be just dVR dt divided by R? I'm going to let you work that out. But the answer is yes. Now, at the beginning of the problem, I said, we've got our 1 amp here, and we're going to open that switch at t equals 0. And then you remember that I started the lecture off by saying, oh, an ideal current source will put out the specified current regardless of what it's connected to. So when it was connected to 4 ohms, we were okay because we had our 1 amp and the voltage was 4 volts and we were right over here somewhere. But we opened that switch and that voltage is going to go shooting up. it's going to actually be over in our neighbor's house or even further. So you can say, hey, wait a minute. What's with this problem here? And I gave you a little cop-out when we started the problem. I said, oh, this current source isn't going to be very happy, but we're not going to worry about it because it's disconnected from the circuit. Okay, but let's look at a better way to draw this so that things are happy. What I'm going to do is draw the current source like this, and I'm going to use the unit step function. And you remember that the unit step function is 0 for any time less than 0, and it's going to be unity at any time above 0. And in order to reverse that so that it is unity before 0 and turned off after 0, I'm going to just call it u of negative t. So let's look at our current source. Current source is going to be sitting there generating 1 amp up until time equals 0. And then at time equals 0, it's going to generate 0 amps. And remember, when we disable a current source, in fact, let's go over here so we can see it better. When I disable a current source, then my line here goes down to 0. And that means that no matter what voltage you put across that current source, you're going to get no current. Isn't that like an open circuit? Again, we started off with our current source at 1 amp. We're going to disable it, which means mathematically we say 0 amps. So let's put it on our plot here. The current went down to 0. So that means I can now, the current source will do what it always does. It'll give you the specified current of 0 amps regardless of the voltage. So I can put whatever voltage I want across that current source, and I'm going to get 0 amps. Isn't that what an open circuit does? Isn't that what a bazillion ohm resistor does? Since we're here just for fun, let's say, what happens when you disable a voltage source? Well, here's our voltage source. Here it's putting out 5 volts, but let's disable it by saying it's only going to put out 0 volts. So at 0 volts, I'm going to shift my line all the way over here to 0. Now I get 0 volts regardless of the current. And I think 0 volts regardless of the current, that's a short circuit. Make sure you're good with these concepts. They'll really help you. Our next example gets a little bit harder. So in this case, looks like we have an inductor and a capacitor this time, and we put our switch up here. So the switch is going to be open at t equals 0 minus, then we're going to close it. And we've got a voltage source here, so it's just going to put out all the current it needs to keep that voltage at 24 volts. Let's take a look. The current at 0 minus, if it says I, you better be able to find I here. And here it is. And at 0 minus, let's look at what's going on. So the switch is open. So let's see, I start at 24 and I got no voltage across the inductor because I'm at steady state. So I'm 24 volts here. And let's see, I got no current through the capacitor. So I got 24 volts here and it goes right through that 2 ohms because I got no current here. So 24 divided by 10 plus 2 is 24 divided by 12 is going to give me 2 amps at t equals 0 minus. And now let's get V at 0 minus. Well, we know the topology, which is this looks just like a voltage divider to us. Try to not put your little stubby thing here, and try not to put your little short circuit stubby thing across here. Just remember, no voltage, no current. And you can see that I end up with just a voltage divider as far as getting V. It's just going to be 2 divided by 10 plus 2 times 24, and that gives me 4 volts right here at T equals 0 minus. Now let's get di dt at T equals 0 plus. And so I'm going to use the formula V equals L di dt. And so I'm doing that because my I is going right through my inductor. So di dt is equal to V sub L at 0 plus divided by L. Okay, so to get that, I need V sub L. And what we're going to do here is we're just going to figure it out. So at T equals 0 minus, I know that I have 4 volts on the capacitor, and that will not change. That will not change at T equals 0 plus. And I know that I have, let's see, I have 2 amps through this inductor. So let's take a look. We don't even need that 2 amps actually. At T equals 0 plus, I have 4 volts here. Switch closes, so I have 4 volts here. This is a voltage source. So the voltage across the inductor is going to be 24 minus 4 is 20 volts. So that means I'm going to put my 20 right here for VL at 0 plus, divided by L, and I have my answer. So here's what we did. VC at 0 plus equaled VC at 0 minus equals 4 volts. Then we closed the switch, and we got the voltage across the inductor, and it's 24 minus 4 gives us 20 volts. So di dt equals V sub L divided by L is 20 divided by 0.4, and that is going to be 50 amps per second. Do we like that sign? Let's take a look. Well, I'm shorting out this resistor, so I know we're certainly going to end up with more current at T equals infinity, because the current at T equals infinity is just going to be 24 divided by 2. It's going to be 12 amps. So it kind of makes sense that di dt is going to be going up, and so that 50 amps per second makes sense to me. Okay, now I want to find dV dt. Or in other words, I want to find dV dt at time equals 0 plus. So it's getting a little complicated, a little harder here. So let's see. At time equals 0 plus, well, let's look at time equals 0 minus first. And here's what it looked like because the switch was open and the 10 ohms was in the circuit. So we know there's no current in the capacitor, and we have our 4 volts here. Now let's look at T equals 0 plus. So at T equals 0 plus, I'm going to keep my 4 volts here. So that is going to mean that I'm going to have 2 amps going this way into this resistor. And I know that I can't change this inductor current quickly. So let's look at that with KCL. I got 2 amps going this way. I got 2 amps going this way. That leaves no amps going here. So my capacitor current is going to be equal to 0 at t equals 0 plus. So dV dt is going to be I over C, which is going to be 0 over C, which is 0 volts per second. Little tricky, make sure you're good with this. Voltage at the capacitor was 4 volts. It can't change. So that means there's 4 volts here, there's 2 amps here. Here I have 2 amps because I can't change my inductor current quickly. So this 2 amps and this 2 amps leaves me nothing here. So I got no current in that capacitor. That means I got no dV dt. Now let's look at I of infinity. So at infinity, we know that it's steady state, and so there's no voltage across this inductor. So I'm 24 volts, 24 volts, 24 divided by 2 is 12 amps. V of infinity, which was right here, is going to be, let's see, 24, no voltage loss, 24. V of infinity is going to be 24 volts. Let's move to our next problem. So now I have a current source and I'm representing it using the unit step function. So what this means is that at time equals 0 minus, there is no current coming from this current source. And as we mentioned about 10 minutes back in the lecture, we said if you disable a current source or you set its current to 0, it looks like an open circuit. So this thing is going to go from an open circuit to a current source of 4 amps. Or if you want, formally, you can say a current source of 0 amps to a current source of 4 amps. Both ways work. So let's see, we've got a 6 amp current source here. I did not show the ground symbol, so I better not ask for V right here because there's no reference for it. But looks like I didn't. Looks like the voltages are very clearly described that we're asking for. So what else do I see? Let's see. I don't know if you watch baseball or not, but you know how they use the term the pitcher threw a big old hanging curveball at the hitter, and the hitter saw that hanging curveball coming and knocked it out of the park. So I kind of use that expression, that's a big hanging curveball. And I see a hanging curveball right in this problem. I see a current source in parallel. Actually, I take that back, my mistake. The hanging curveball, which is going to be basically a Thevenin source, is in one of our next problems. So scratch that part, but don't scratch the hanging curveball part, because you'll hear me say that over and over again. Okay, so at t equals 0, I know I'm going to have no voltage across this inductor. So that means I'm going to have 0 volts here. Let's pretend like there's a ground symbol here. So I can say I have 0 volts here. And the capacitor has no current through it at t equals 0. So I got no current here. This is turned off, so I got no current here. That means I got no current here. So I got no voltage drop across this 5 ohm resistor. So that means I'm 0 volts here, and I go up 0 amps times 5 ohms. I got 0 volts here. So 0 volts. And if I visualize this circuit, I see the 6 amps going through that inductor. And there's no voltage across it. Okay, so I sub L at 0 minus is obviously going to be negative 6 amps. And I sub L at 0 plus is going to be equal to I sub L at 0 minus, which is also going to be negative 6 amps. So the voltage at the capacitor at 0 minus, we said was going to be 0, because remember, this was 0 volts because there's no voltage across the inductor. And we know that there's no current through this resistor because that current is 0, because it's a capacitor at steady state. This current is 0 because the current source is disabled. So this current is 0, so 0 plus 0 times 5 gives us 0 volts here. So VC at 0 minus equals VC at 0 plus is equal to 0 volts. VR at 0 plus is going to be, well, let's look at this. What's the voltage across this resistor at 0 plus? So in order to get that, we got to figure out what happens when this turns on. And I'm going to go to the rules, and I'm going to say that you can't change the capacitor voltage instantaneously. It's one of our rules. But then another of our rules that's going to give us some comfort here is that you can change the capacitor current quickly. Yeah, I know you woke up. Don't bug me. You can change the capacitor current quickly. So what's going to happen is, actually, let's do even more. So we know we can change the capacitor current quickly. Now, we know that we can't change this current quickly, and we certainly can't change this current quickly. So at t equals 0 plus, I'm going to have 6 amps going that way, 6 amps going that way. I'm going to have 0 amps going that way. So that tells me that all this current is going to go into the capacitor because I got no current going this way. Circuit won't allow it over here. So all that step current is going to go into the cap, and as we said, there's no current in the resistor at t equals 0 plus, so VR at 0 plus is going to be 0 volts. So now, realizing that all that step current goes into the cap, what's dI L dt? Do you want out? What Bella doesn't like is the door being closed. She likes the door being open so she has the option to go in and out, though she rarely ever goes out. She just likes the door open and she complains about it if it isn't. Okay, so for dIL dt, we are going to say that is equal to the inductor voltage divided by the inductance. And this inductor voltage at t equals 0 plus is going to be 0 because the current does not change at time equals 0. I'm sorry, the voltage doesn't change at time equals 0 because remember, there's no current going through this path right here. So dIL dt is equal to 0. dVc dt, that is, for that, we're going to use our equation that says I equals C dV dt, and we're going to solve it for dV dt. And that's going to be just the capacitor current divided by the capacitance. And we said that all that step current goes into this capacitor. So that means we're going to have 4 amps going into the capacitor. and 4 divided by 1/5 is going to give us 20 volts per second. Now we want to get dVr dt at 0 plus. This is a little tricky. At t equals 0 plus, we know that this current source is going to turn on, but we're going to have no voltage on the left side of this resistor. And so that means that there's going to be nothing changed over on this side of the circuit because this voltage started at 0, it stayed at 0. And so therefore, we're not going to get any voltage across the inductor. And remember that V equals L di dt. So if voltage across the inductor at time equals 0 is 0, then di dt is equal to 0. So di dt is 0 for the inductor. Of course, di dt is 0 for the source. So that means that di dt for this resistor is also going to be 0. And if di dt is 0, then dV dt is 0 for the resistor. That's a tough one. So now let's come down here where I said dVr dt was 20 volts per second. So scratch that out and then scratch this out. And if we weren't in the middle of this COVID-19 lockout and I could get to my binders in my office, I would update this lecture, but I'm not able to do that. So cross that out. It's 0 volts per second. Okay, so now let's get I sub L of infinity. So at t equals infinity, we've got a pretty complicated circuit, but we can use the rules to make things a little easier. So I know that at steady state and at infinity, remember this is on, I got 4 amps. None of it's going through here. So that means it's all going this way. So I got 4 amps going that way, and I got 6 amps going that way. So KCL on the fly is going to say 4 go in, 6 go out. That means 2 got to be going this way. So I sub L at t equals infinity should be negative 2 amps. Now let's get the capacitor voltage at time equals infinity. So let's see, at time equals infinity, we know the voltage here is going to be 0 because there's no voltage across this inductor. So that means I have 4 amps, none of it's going this way. Oh, it's all going through the 5 ohm resistor. So 4 times 5 is going to be 20 volts from here to here. Now I know that I'm going to start at 0, go up 0, go up 20, and I'm at 20 volts. Or in other words, I guess I could have just said VR from plus to minus is going to be just 4 amps times 5 ohms, or 20 volts. And VR at infinity, actually, sorry, that's just what we did. But let's look at VC at infinity. Well, we know that we are at 0, 0, go up 20. VC of infinity is 20 volts. Okay, moving to our next example, let's take a look. We've got our ground symbol here, and we've got a 12-volt source. I see a switch that is going to open at t equals 0. So that means it's closed before then. So I definitely know I'm going to have no voltage across the capacitor at t equals 0 minus. And we're going to open that switch. And let's see, when we do that, all that current that was going from here and through the inductor since the inductor will insist that the current can't be changed, all that current's going to go into the capacitor. However, the capacitor voltage will remain 0 across the capacitor. So let's see, at t equals 0 minus, I'm going to have 12 divided by 2, or 6 amps. Why do I have that? Because, of course, the voltage here is 0. There's no voltage across the inductor, so I'm 0 here. I'm 0 volts here. So my current is going to be 12 divided by 2 is going to be 6 amps. And at t equals 0 plus, that's not going to change. So what that means is that I'm still going to have 0 volts here because I'm going to still have my 2 amps, or I'm sorry, my 6 amps. Okay, so I think I get this. So V sub L at 0 minus, we know that's going to be 0 because it's connected to ground and there's no voltage across that inductor steady state. I sub L at 0, that is, we're going to have 0 volts here, 0 volts here, 0 volts here. So I sub L at 0 minus is going to be 12 divided by 2 equals 6 amps. I sub L at 0 plus is simply equal to I sub L of 0 minus, so that's also going to be 6 amps. IC at 0 minus is going to be obviously 0, because 0 minus is a steady state condition and we don't have any current in the capacitor during steady state. Now IC at 0 plus, we know that we can change that capacitor current quickly. So let's see. We know that we can't change the inductor current quickly, and that inductor current was 6 amps. So the 6 amps that was going here now has to go through the capacitor because the switch opens. So that means IC at 0 plus is 6 amps. So we started with IC of 0, and then it went to 6 amps immediately. And we remember that we can change the voltage across the current through the capacitor quickly. VC at 0 was 0 because the switch was closed. And so, of course, it was shorted out. And we can't change the voltage across the capacitor quickly, so VC at 0 plus is also going to be 0. So VL at 0 minus, we know is going to be 0 because at steady state there's no voltage across the inductor. But what is it at 0 plus? We know it. The inductor voltage can change quickly, but what's it going to be? Well, we know that the current won't change, so that means that this current won't change. So let's see, 12 minus 2 times ohms times 6 amps is going to give me 0 volts here. And I know that I had 0 volts across the capacitor at t equals 0 minus, so I'll have 0 volts across it at t equals 0 plus. So the voltage at the inductor will remain 0. It could change quickly, but it didn't. dVc dt. We know that I equals C dV dt. So dV dt is going to be I over C. And we know we have 6 amps at t equals 0 plus going through the capacitor. So dVc dt is going to be I over C is going to be 6 amps divided by 2 farads is going to be 3 volts per second. DIL dt. We just determined that the voltage across the inductor at t equals 0 plus is going to be 0. So V equals L di dt. So di dt is going to be V over L, which is going to be 0 over L is going to be 0 amps per second. Finally, let's get the inductor voltage. Sorry, not finally. The inductor voltage at time equals infinity, V sub L. Start at 0, go up 0 because there's no voltage across the inductor at steady state, and VL at time infinity is equal to 0. VC at infinity. So at time equals infinity, I'm going to have no current through the capacitor. So I got no current through the switch because it's open. I have no current through the capacitor. So let's see. So that means that there's no current in this resistor, just using KCL on the fly. No current here, can't be any current here. So that means 12 volts minus 2 times 0 gives me 12 volts here. And the voltage here is going to be 0 because there's no voltage across that inductor at steady state. So 12 minus 0 gives me 12 volts for VC of infinity. Moving on to our next problem, let's take a look at the circuit. We've got a voltage source here, and we're using the unit step function to describe the change in topology that we call it at t equals 0. And here it's 4 times u of negative t, meaning that this source is on until time equals 0, and then it turns off. And remember, when a voltage source turns off, it becomes a short circuit. So I just drew a little picture here because that kind of helps keep things clear in my mind. And now I look over here and I see a current source of 4 times u of t amps. And it's in parallel with 5 ohms. So this goes back to my baseball analogy of I see a big old hanging curveball in front of me. And when I see a current source in parallel with a voltage source, I immediately always think, what does the Thevenin equivalent look like? Because the Thevenin equivalent might just make it easier for me to solve the problem. Similarly, if I see a voltage source in series with some Thevenin resistance or impedance, as we'll get into later in the course, I want to look at it as a Norton source because that may make the problem easier for me. So in this case, I'm going to take these 2 components and I'm going to make them into a Thevenin source to make my problem look easier. That's pretty easy to do. 4 u sub t amps multiplied by 5 ohms gives us our open circuit Thevenin voltage, meaning the voltage we'd have if there was nothing connected here. So 4 times 5 gives me 20 u of t. And a good rule you can always remember is that the Thevenin and Norton impedances are always going to be the same. So I'm just going to slap my 5 ohms right here. And the circuit looks a little easier to me now. And I'm going to draw another little picture just to show what this voltage source is doing. So that's my first simplification. At t equals 0, I'm going to draw the circuit at t equals 0 minus, At t equals 0 minus, I know this just looks like a voltage source of 4 volts, and this looks like a short circuit, because that's what a voltage source looks like when it's disabled. And so here it is. At t equals 0 minus, we have the 4 volt source, and then we have that 5 ohms going to ground. And you can see I just kind of drew it this way. And now I'm doing what I often tell you guys not to do, which is since I'm at t equals 0, I pulled the capacitor out. So Do as I say, not as I do. So now I've simplified the circuit even further, and I've still got my supply, I've got my 3 ohm resistor, I shorted out the inductor because there's no voltage across it at steady state, and I opened my capacitor and I just see a voltage divider. So I'm going to say that the voltage is going to be 5 over 5 plus 3 times 4 volts is 2.5 volts. And I, this current, is just going to be 4 volts divided by 8 ohms is a half an amp. And we notice that we remember that V of 0 plus for the capacitor, right here, V at 0 plus is going to be equal to V at 0 minus. And also, I at 0 plus is equal to I of 0 minus. I can't see that here, but I can see it here, and that's why I usually kind of like to leave these in. So these are just 2 of our rules that are going to help us. Now let's draw the circuit at t equals 0 plus. What you see is that this power supply has turned off, so its voltage went to 0, or in other words, this power supply at t equals 0 goes to 0 volts, so that means that it's essentially a short here. And this power supply turns on. So I've just drawn my components here. My short circuit is right here, and my power supply is on. And I need to remember what my conditions from t equals 0 minus were, so I just wrote them down. I at 0 plus is equal to I of 0 minus is equal to a half an amp. V at 0 plus is equal to V at 0 minus, which is 2.5 volts. So I'm looking at this instant of t equals 0 plus. And what I can say is the current in the 5 ohm resistor here is going to be 20 minus 2.5, because that's what the capacitor voltage is, divided by 5 ohms, is 3.5 amps. And the current in the capacitor, how am I going to get that? I'm going to say, well, I know I have 3.5 amps coming this way because I just figured that out. But remember, I know that I have a half an amp in this inductor, and that's not going to change. So I got a half amp going that way. I got 3.5 amps going that way. That's going to give me 4 amps in that capacitor. So I can easily find dVc dt. It's just going to be IC over C, which is 4 divided by 0.1 is 40 volts per second. Now let's find di dt for this inductor, or di dt, which is the current that goes through the inductor. And to do that, I'm going to actually draw myself a little drawing here. I know that the inductor current is going to be a half an amp at t equals 0 plus, and I know that the capacitor voltage is 2.5 volts. And remember, to find di dt, what I really need to do is get the voltage across the inductor, because V equals L di dt, so di dt is V over L. So what I really need is this voltage. So let's see. KVL on the fly says that I've got a half ampere, so I'm going to start at 0, and I'm going to go down a half an amp times 3 ohms. That's negative 1.5 volts here. And I know I got 2.5 volts here. So what's the voltage across the inductor? It is going to be this voltage minus this voltage, which is going to be negative 1.5 minus 2.5 is going to be negative 4 volts across that inductor. So V sub L is equal to L di dt. So di dt is V sub L over L is negative 4 over 0.25 is minus 16 amps per second. So you can see here that things just got a little complicated for me. So I did what engineers do. I drew a picture and I made it simple. And then we got the answer. Now let's go to t equals infinity. And I'm going to draw another picture here. And I'm going to say that my 20 volt source is on. My other source over here is off. So of course it's shorted. And let's figure out what we have. So V at infinity is going to be 3 divided by 3 plus 5 times 20 is 7.5 volts. I didn't need to take these components out. I know I got no voltage here and I got no current here. That's all I got to remember. So I'm not going to take those components out. I at infinity is going to be it's going to be negative 20 volts divided by 8, or in other words, minus 2.5 amps. Now, what I might encourage you to do, if you really want to make sure you understand this stuff, is go right back up to the top and work the problem without using the Thevenin equivalent. Work it using that current source. You'll get the same answers if you do it right, but it will give you some really good practice because a lot of some of the techniques you use to do the problems will change a little bit, but you'll still just be using the rules. So, a lot of material in this lecture. I hope it really helps you. On the one hand, it's one of the most difficult sets of concepts and problems in the course. On the other hand, this is the most useful circuit stuff you're going to see. Especially if you're taking this course before you take 330, this is going to make EE 330 so much easier for you. So, as always, I hope I see you in office hours, and if not, I'll see you in the next lecture.